let me pull up. Okay, so in our recommended reading, we have a couple links about sheet metal, one of which is the 148, how they build sheet metal. So this is kind of the CNC process. Like, this is very similar to how our sponsor does it. When our sponsors actually do sheet metal with a laser cutter and a CNC brake, and they kind of walk you through it. They add a little bit of stuff. They have a turret punch, which our sponsor doesn't have. There's a few other machines that they can have to make the process a little bit easier. But if you have a sponsor doing your sheet metal, it's definitely a much more expensive process for the equipment involved. But there are things that we can do in our shop, and that's what we're going to talk about for the rest of this after we show this, to make sure we have an idea of what the sheet metal process is. Why don't I have audio? You guys don't hear anything, right?
No.
Okay. Okay, back to here.
Of Greenville, Texas, and the Thunder Chickens of Sterling Heights, Michigan have something in common. Their robots are well known within FRC for their distinctive look. This look comes from their almost exclusive sheet metal construction. Today on How It's Made, we're going to learn how this sheet metal is fabricated. After the team has finished their brainstorming and has made prototypes of their major concepts, the design team begins its work. It is their job to CAD the entire robot down to the smallest detail. Using the sheet metal features found in the 3D modeling program SolidWorks, each part is drawn as it will appear on the final robot. These parts are then flattened into flat pieces, which are sent to the sheet metal shop for production. Though the sheet metal shop is a CAD to master facility that directly imports the CAD models for production, drawings need to be done to show the brake operators how to bend the parts. Let's step inside the Innovation First International Fabrication House, Metal Solutions. Flat patterns of parts are imported so they can be programmed for production on the CNC laser cutter or turret punch. Every part starts as part of a 4x8 sheet of material. Typically, the Robo-Wrangler and Thunder Chicken parts are made out of Lexan or aluminum. The laser cutter and turret punch has a material loader. It can hold enough material such that the machine can run for almost 60 hours without any human intervention. Flat sheets go in, finished parts come out. Here you can see the laser cutter cutting the outline of a part that will appear on the 2010 Robo-Wrangler robot. The CNC turret punch operates just like a 3-hole punch. Instead of cutting through paper, it uses 40 tons to punch right through metal. Here, you see the metal slugs that are punched out the bottom by the turret punch. These are dumped into a bin and then set off to the scrapyard for recycling. Flat parts are still held in place on the sheet by something called shaker tabs. The parts need to be removed from the sheet before they can be bent. These shaker tabs, however, will leave burrs on the part that need to be removed. Here you see one of the deburb guys grinding off the shaker tabs. Each part is fed through the automatic deburring machine. This machine sands down all the edges, and puts a nice finish on each face. After being deburred, the parts go off to the brakes where they'll be bent into shape. Here you see the top and bottom die of a brake. To begin with, the operator takes the flat part and the drawing and has to program the CNC brake. He needs to tune the machine for each individual part such that it is bent the correct amount. Tuning the machine to get the parts just right takes a large amount of skill. After the first part is finished and the machine is programmed and tuned in, all the remaining parts take very little time to produce. Once the parts are finished being bent, threaded inserts are pressed into them. Completed parts are placed on a pallet and sent back to the team for assembly or out for powder coating. Thanks for joining us today on How It's Made. Tune in next time to find out how the Simbots make.
Okay. So like I said, so that's how the industrial process works. And one of the things to notice is all those parts, there's multiple people involved at their place to make them, right? There's someone who has to operate the laser. There's someone who has to operate the brakes. There's people moving those parts from place to place. They have to like keep track of them. It's a lot of work to support an FRC team with sponsored sheet metal. So that's why we're very grateful to Solarcraft for doing it for us. And it's understandable sometimes when things are off, especially if we don't communicate well. Like they showed in like their drawing, like we have to give them the drawings for the bends. If we make an error in that drawing at all, the bend's going to be wrong because they program straight off that drawing that we produce. There's a lot of things that can go wrong when we're not involved in the process at all, where we just basically send it to them and hope it comes back correctly. Most of the time we do a pretty good job and it works. It doesn't always work. The next link in the recommended reading for sheet metal is a new one that I found from this company who does production work for other people. My laptop is being weird. Let me see if I can get this better. Okay. But it has a good idea of kind of going over the basics of why you'd even want to do sheet metal, right? There's there's a lot of different ways we could build parts on our robot. None of them have to be sheet metal. Sheet metal is just one of the tools, or bent sheet metal is just one of the tools that we can use to fabricate something and get the function that we want. And sometimes we can make it, one of the big benefits is you can use a thinner sheet and put flanges on it to add, just like as you fold a piece of paper, you can make it stronger than if it's just a piece of flat paper, it's going to bend everywhere. As you start putting creases into it, you fold into like a box, it's a lot harder to bend. The same applies to sheet metal, so we can use much thinner sheet metal than if we were just going to use a flat plate. What am I looking at? So yeah, so there's a few different, the press brake is the type that they have at Solarcraft. We don't have a very large press brake. They're going to be a lot of money to have anything that's anywhere close to that. The brake we have in our shop is what's called a box and pan brake, where we have to lift the skirt to actually do the bending. It still works. It allows us to get, it allows us to set pretty decent bends. We can bend relatively thick material with it. Ours is big enough that we can do 1/8 inch aluminum if we need to. But a lot of what we want to be able to do is bend thinner aluminum and bend polycarbonate too, to be able to use thin polycarb in places and get some of that rigidity back that polycarbonate doesn't inherently have compared to aluminum, right? It's a lot easier to bend the plastic sheet than it is to bend an aluminum sheet. But by adding flanges, we can make it stiffer and less likely to bend. Kind of the basics up at the top are just how it actually presses the die in to actually fully form the 90-degree bend. Most time, anytime you're changing the shape of a piece of sheet metal, it's called forming. So that for what we're doing, we're basically just always using a press brake or a normal brake to do bends. In industry, they'll have form tools that are a lot more expensive, but they can just press right in and get full shapes and things out of a piece of aluminum. So a lot of like automotive car panels and stuff are made that way. Very rarely would that be needed for FRC robots, since we're not making thousands of the same part over and over again. We're only making a few. Bending is reasonable to do a few times and still get consistent parts. Making an entire press form or anything like that is probably not useful. When we're actually CADing in SolidWorks, we CAD the bent part, and then we have to tell SolidWorks how the metal is going to deform so that it can figure out how to make a flattened part for us. So we'll CAD it up to where we have different flanges, we'll CAD in the bends, and then one of the things we have to do is tell it however the process we're going to be using to bend the metal, how it deforms the metal so it knows how long the flat part's going to be. Because when you actually bend it, it's not like this, the lengths of the metal don't actually stay the same, right? You're forming it by actually deforming the metal in some way. So when you bend, if you were to like kind of trace this line and measure how long it is right across the top edge of this material, the outside edge, it's going to be longer than this inside edge. Just like if you were going around like a racetrack or anything, the outside edge is going to be longer than the inside edge. Okay. My computer is getting back up, I think, so I'll be doing that while I do this. Okay. Does that make sense that the outside edge has to stretch and the inside edge has to compress? So the way it does that is a little bit different based on like how much it stretches and how much it compresses is different based on the material, and also different based on the machine you're using to actually bend the part, because you get a different, you also get a different bend radius, because you can have it, right? In theory, you could take a big piece of aluminum and bend it over a really big arc, or you can bend it over a pretty small arc. And that kind of depends on the tooling and the brake that you're using. So with different press brakes, you can have different dies that set different bend radiuses. With the box and pan brake, you can do a little bit to change radius, kind of depending on where you clamp and how the teeth are. So we can set that bend radius for our parts kind of based on how we set up our brake. And then we'll need to be able to use that. We'll have like some rough idea of that number that we can give to SolidWorks if we're trying to make accurate bends, where we know the length of this flange for sure. There are times where we may not, that's one of the things we need to try to start figuring out this year, is to be able to design parts where we don't necessarily need to know the exact length of this flange to make accurate bends or to make accurate parts for what we need. We can do different parts of our design differently to not have us need to be as accurate as like the CNC brake at Solarcraft can get us, but we can do a lot of our own bending and still be accurate enough to still allow for some value. How broken is it going to be when I join the Zoom again twice? Okay. Okay. Can you hear my second me?
Yeah.
Okay. Interesting. Now the question is, if I stop sharing, okay, and figure out how to have a keyboard here where my laptop is, because that's still recording. Okay. This is getting complicated. Back to where we were. And all right, back to where we were. And I can actually see what we're doing again because I'm not on weird laptop and Zoom. Okay, so as we were talking about the bending, right? So you have this inner radius, which is your bend radius. Angle of the bend is pretty obvious. The important thing is that, like I said, the outside's going to stretch, the inside's going to compress. This line right here through the middle that they call the neutral axis is not actually always in the exact middle. Sometimes it's going to be closer to the inside edge. Sometimes it's going to be closer to the outside edge. And that's part of what you're trying to learn with the K-factor, is that it can move around a little bit of where exactly that line is. So that's all part of like the measurements you take. The way we do it the way we used to do it for Solarcraft is they would actually like bend samples of the part and figure out how much they stretched. So they would take like a 6-inch piece, bend it in the middle, and then measure the two outside faces and be like, okay, now this is 6 1/8 or something, and that's how much it stretched. And we would type in that number for our bend deduction, like the number of how much it actually added to the material. They moved away from that. Now they're starting to do everything with K-factor for us, and it works well enough. And K-factor is basically showing the location of the neutral axis in the material, calculated in relation to the material thickness. We don't really need to worry about how to calculate K-factor for what we're doing. We're not going to be doing that very often. We may have to do it for, we may have to do it depending on if we're using our own brakes and if we need to like figure out how to program it into SolidWorks to do the bending, or into Onshape for some of our bending. But largely, we shouldn't have to worry too much about calculating our own K-factor. Just know that K-factor is one of the things that if you're ever doing this for your job or something and you're making sheet metal parts, ideally the machine shop is going to give you either K-factor or bend deduction. There's some other things they can give you that work too. Bend allowance works. That you can kind of get enough information that the CAD software can figure out how to flatten the part properly. Okay. Yeah, we already talked about bend radius a little bit.
Oh my God. No sister?
Spring back is useful. So all the materials that we bend are elastic, including aluminum. So as you go to bend, you have to bend it slightly further than 90 degrees if you want an actual 90-degree bend. Because when you let go, the material is going to try to like expand back out. This is especially true with polycarbonate. The plastic, you can bend thin polycarb very easily cold, and it will bend over just fine. But if you try to like bend to 90 and stop, it's only going to be at like a 45-degree angle or so. So you have to bend it further and then watch and feel and kind of like see how far it springs back, and then go a little farther past it and do it again. Okay.
Wow. You go for crypto, of course. The Lost Treasures collection delivers a bunch of exclusive content you can earn.
Yeah, is someone watching like a show?
Yeah, what is happening?
And the introduction.
Nicholas, is that your audio?
He's still watching a show.
A trophy of himself.
Being somebody.
See you all in the ring. Don't worry, there's plenty of games to go around.
I'm pretty sure you could force me to because you're host.
Yeah, I
Well, I
think
know,
Nick's
but-
watching a
Well,
show.
but I'm not okay. I wasn't
Me
host
neither.
on I wasn't host on my main PC, which is a different problem. Wait, this one doesn't have its camera on? Now I'm just even more confused. Start video. Okay, now there's
And
two.
there's two of you.
This whole thing is confusing. Stop video.
Oh.
And okay, this is gonna be a weird pause in this video. Make host. Oh wait, no, I don't want to make that host yet because I think the recording gets messed up if I do that. Okay. Right. Okay. So minimum bend radius and minimum flange length are basically minimum bend radius. A lot of times is based on the material. It would make sense that you can't have an infinitely small bend radius because then you're putting like a sharp corner in the material, and almost every material is going to crack if you try to do that. So you need to have some amount of a radius there. Their recommendation down here on this webpage is that the radius should be at least 1 times the material thickness. So if we're using a piece of 1/8 inch aluminum, you wouldn't want a bend radius smaller than 1/8 of an inch. If you're using 090 aluminum, 0.09, you wouldn't want a bend radius smaller than 0.09 of an inch. Our bend radius through Solarcraft is 0.118 for most things. That's the break they use, sets that radius for us. Minimum flange length is also important. There's they have like a whole chart to figure out what the minimum flange length is. Do they actually go through, do they give a formula on this one? I haven't looked through this one as much. So sometimes it depends on like your other flange too, depending on which side the brake can actually clamp on and things like that. But we've pushed Solarcraft a little bit. There have been a few of our flanges that have been really small, and we've asked them to bend them. It's something close to at least like bend radius plus material thickness or so is the absolute minimum. But you normally want to have a slightly bigger flange than if you can do it. There are spots where we've needed tiny flanges, like the outer bends on our drivetrain where we bend out kind of towards our bumpers. We've tried to get those really small the past 2 seasons. Okay. There's a few other things that we don't need to go too far into. Largely, we almost never make bends like this where they're like sucked into a part where you have to have this like weird, these cutouts in here. We try to avoid designing those to where you just have a nice clean bend on the edge of the part instead. It's easy enough for us to do that in design. And we almost never need that little extra material sticking out or anything like that. So almost all of our bends are always to the outside. I'm going to pull up SolidWorks in a second and kind of walk through this. We also rarely have to do the notch thing. We try to go through and just eliminate all this extra material too. The gap in here doesn't hurt us very often. So if we do have to have two bends next to each other, they just end up with a slightly larger gap most of the time. It's just easier to bend that way when they're actually doing it. Okay, yeah, so their bend height, yeah, so they say twice the thickness plus radius. Sometimes you can go a little bit smaller than that. It depends on the machine. But yeah, you'd want that, you want the radius, you want the flange length here to be at least reasonably big so the machine can actually press it and not just like deform this and actually get a solid bend through there. You don't want to have holes too close to bends because they'll deform. They won't be circular anymore. They'll basically, as the bend happens, the material is stretching like we talked about earlier, and it'll stretch where the hole is and make it this weird like non-circular hole. Sometimes that's okay. We've had to do it on occasion and just told Solarcraft, yeah, we know it's going to deform. Just let it happen. But we try to avoid it when we can so we can keep reasonably nice holes. Same with distance to the edge. So what happens here is you'll get like really weird. If this is too small and you try to stretch it, it may even rip just because it doesn't have enough material there to just withstand being stretched across the bend that way. So as you get closer, you want to make sure you do have some material there. The minimum hole diameter is based on how you're actually doing the cutting. So if we were cutting it on the laser, there's some small hole that it can do that's very, very small. I think we've had them cut like a 1/16 hole. They did not like that. Don't ask them to do that. We're never doing that anymore. But we've had a part where that was a thing. Because for anytime the laser has to put, the slowest part of actually cutting with the laser is the first puncture in any cut. So tiny holes and just lots of holes is way slower than lots of big cutouts because it has to do the first initial like puncture through the material and then it can keep cutting relatively fast, but that first puncture takes a while. So that's actually one of the negotiations we have with Solarcraft, since they have to laser all of our holes. They don't have a turret punch. Is how many holes can we put in things? How do we design with fewer holes? There's gonna be some stuff that we're gonna try to do more in shop where we can do it on a router or a laser cutter if it can be out of Lexan, so that we can still have holes for adjustability and design things that we need without putting too much of a time sink and using too much of their laser time if we can avoid it. This goes further into some tolerancing for the laser and stuff. Most of it is well within acceptable range for us in FRC. We're not too worried about any of the laser problems. The laser does have kerf. On sheet metal, it's relatively thin. So the actual, so what this is saying is the edge of the material when the laser cuts it isn't actually perpendicular. It's some sort of angle. We notice it a lot more if we're using our laser in our shop and we're cutting through relatively thick material. So like if we're cutting through like 1/2-inch plywood and you look at the edge, you can definitely notice that it's not straight. It's just the way the laser focuses. It focuses a beam down and then it comes back out. So you get like this edge of there's some sort of beam angle there that it's trying to cut through. I'm not going to go through all the curls or anything like that because we don't almost never use them. But just in general, this is a good place to go through and look through to have an idea of how some of the sheet metal works. I'm going to pull up SolidWorks and screen share SolidWorks. Maybe. There we go. Okay. So we're going to do a super basic sheet metal part right now. And then I'm going to pull up the 2014 robot and we're going to go through that for our last little bit. So sheet metal parts in SolidWorks start with a sketch just like normal. For most of the parts we're doing, this is the way we design them. Sometimes there's a different way I can do after this. So we're basically, here we're gonna do a base flange first. So I'm gonna make like a 3 by, maybe I'm gonna make a 3 by something. My keyboard being weird. Okay, a 3 by 3 square. I'm gonna go over to the sheet metal tab. On your SolidWorks installation, if it's the first time you're using sheet metal, sometimes this button isn't here. You have to right click any of these tabs and select sheet metal. It normally doesn't show up in like the default SolidWorks window. So then I'm going to hit base flange tab. And so it's going to turn this into a piece of sheet metal. And I have to give it some parameters. So here I have to tell it the material thickness, and then I have to tell it its K factor, like we talked about earlier, so that it knows how to do the bends once I start adding flanges to it on the outside. So I'm gonna go ahead and tell this that it is 0.09. That's our most standard aluminum sheet metal that we use. And then I'm gonna leave the K factor 0.5 for now because it's not important, but actually if we're doing this for Solarcraft, we have a special gauge table in our GrabCAD folder that we use, that we pull through. So it has all of the settings and everything for you. You don't have to type anything in. You just hit use gauge table, and then when you select the thickness of material, it sets everything for you already, and it's all ready to go. So now I have this 0.09 piece of aluminum, and it's just a square. If I want to add bends to it, we come up here to the edge flange button, and we select any of the edges, and we can pull it up and tell it how long the flange is going to be. So I can tell it, okay, I want a 0.5-inch flange, but that's not all we have to tell it. So we told it we want a 0.5-inch flange, but we have to tell it, what do we mean by a 0.5-inch flange? There's a few different options here. So you can do outer virtual sharps, which means it's measuring from this back side to this top face, like this top edge here. You can do inner virtual sharps. So it's measuring from like this, the whole flat here is gonna be 0.5. Or you can do it from tangent to the bend. In that case, these two are actually identical because the bend was 90 degrees. If the bend isn't 90 degrees, those become different things. Most of the time, we almost are always going to use this outside virtual sharp measurement for this choice. There are times when designing that you need to do something else where like the flange length matters and you're clicking this button. Rarely does that happen. Most of the time, you're just going to leave it alone and use the first one. The next one, however, does matter quite a lot, depending on what you're building. So remember, we started, it was a 3 by 3 square. So the question is, when as a designer, we need to know, did we want the flat part of this piece of metal to stay 3-inch by 3-inch, or did we want the flange to be included in that 3-inch length, right? So right now it's material inside. So from this like top face that's going to be bent here over to here is going to be 3 inches because the material's inside of this plate. If we come over, we can move it to material outside. So now that just means that the inside of this flange to this outside is going to be 3 inches. We also have bend outside, which puts us at the entirety of the bend. So now this whole flat square is back to 3 inches by 3 inches. And then there's other ones that aren't important for 90 degrees because they're basically just the same as ones that already exist. Like the thing does not move for any of those because for 90-degree bends, they're identical. If you're doing some weird bend that isn't 90, it may be important to do that. the vast majority of sheet metal bends that we do on the team are 90 degrees. As many as we can. It's just easier for them at Solarcraft to bend 90 degrees quickly. It's also easier for us to do 90 degrees in our own shop if we have to make them ourselves. So I'm gonna do that one with bend outside. Okay, so that's the that's basically a sheet metal part. You could keep doing that. You can also, if you know you want the same flange on a separate thing, you can collect multiple edges in the same bend. So now if you have like a C channel, if you're building something that needs it on both sides, you can click them. If you needed it all four, you could do it as well, and it'll figure it out for you. So all of those are options. The other thing you can do, which I don't think we go over nearly as often, is if we know the rough geometry of something we want to make. Say we know we want to make some like S piece of thing, and it has different shapes or different lengths. So we want this length to be 1 inch. We want this length to be 3 inches. And this one's going to be different. This one's only going to be like 0.75. So now if this is going to be like this whole S piece of sheet metal, we can come into sheet metal and do new base flange just on those lines. And it'll let us set a length here for however long we want. Say we want a 10-inch piece of this. Maybe. What's it doing? Oh, that's thickness. I hit the wrong button. Direction 1. This is what I wanted. Okay. 10. So now you don't have to go in and make both edge flanges. You don't have to like set everything up. It already did it for you based on how you drew it. It does matter kind of which way the material is, so you can flip which direction the material is in if you need to. That normally doesn't affect much, but depending on how you're drawing it, it may matter. But you're basically just drawing one side of your entire part, the entire profile of your part, and then it'll do the rest for you. And it'll add in the right bend radiuses and everything. So sometimes that's faster than making a base flange and adding flanges. It just kind of depends on what we're drawing. If you're trying to do it, but if you're trying to connect two different things, this might be faster.
Wait, so would the line you drew in the sketch be like in the center of that part?
No, it's one of the sizes. It's one of the sides. So it's either the inside or the outside.
Okay,
right. So right now I have it. The line I drew is this bottom side, however you want to talk about it, right? It's this piece of aluminum. If I hit the reverse direction button, it flips to the top side.
Okay, I got you.
Yeah, so you get to choose which one you're looking at. So it's a little awkward though, because if you were trying to connect between two things, right, you would need to, and it was like this S bend, you would need to draw it, and this would be 0.09 away from the thing you knew you were going to have to touch, right? If we were trying to make it do that. If it was just a C, it becomes much easier, right? This doesn't have to be it doesn't have to be an S. It could just be the L if you want to do it that way. It can also be a C. So if you did that, this makes a little bit more sense. Now you're just drawing the entire outside of that C. There. Right, so now it's the outside of that C, and we know this face to that face is exactly 3 inches. If you reverse this one, it goes the other way, and now this whole thing got bigger, but now we know the inside of this is 3 inches. Does that make sense?
Yeah. Okay.
Okay, so how do we use sheet metal to actually build a robot. I'm gonna go